Good evening everyone. Today we are going to see about the calculation of overhead costs incurred during a product manufacturing. And before startup of today's video, I wish you all happy Ugadi. Basically, the overhead costs are going to be incurred by three things. Like the major attributions are going to be about the heat loads, like due to the heat loads. And second thing is due to the power consumption by the equipments. And the third one is due to the manpower. These three things. And apart from that there will be few other things will be available, and based on the requirement, so we have to take those things into consideration. And first of all, let's start with the heat loads. And today the process that I'm going to select is having few operations which involves heat transfer. So we need to consider only the operations which are involving in heat transfer. So I'll mention those things. Like the first step is, the first column is going to be operations. And today the template that we are going to show you is going to be somewhat detailed. And the second one is reaction mass, like the quantity, and here it is going to be in liters, and here this is going to be in kgs. The next thing is density, it will be in kg per meter cube. And the next one is specific heat. The next one is temperature difference, nothing but delta T. Next one is latent heat, the units are kilocalorie per kg. Next one is sensible heat load, this is going to be in kilocalories. Next one is latent heat load, this is going to be again in kilocalories. The next one is total heat load, this one in kilocalories. And here it is the steam consumption, this will be in kgs. Next one is cooling capacity, this will be in tr. The operations that are available in the processor, like which involves only heat transfer. First thing is heat the reaction mass to 70 degrees from 30 degrees. This is the first heat transfer operation. And the next one is distill out solvent completely under vacuum below 50 degrees centigrade. This is the second heat transfer operation. And the third one is cool the reaction mass residue to 30 degrees, or else simply cool the reaction mass to 30 degrees centigrade. The next one is heat the reaction mass to 50 degrees from 30 degrees. The next one is cool the reaction mass to 0 to 5 degrees. So simply these are going to be the heat transfer operations. And the quantities, for instance, I will be considering as 1000 liters. And coming to this gauges, so we don't know exactly, so initially we have to make a note of these densities. So I'll consider this as water. Okay, so automatically what will happen is, as this is going to be water, the density is going to be 1000 kg per meter cube, and the volume is equals to the mass divided by 1000, and the specific heat is going to be 1 here. And for any type of reaction mass, if you don't know the specific heat, you can take the value as 0.5 kilocalorie per kg degree centigrade. Since it's an organic mass, it is going to be approx 0.5 kilocalorie. And here this is going to be 40 degrees delta T. Why? Because we are going to raise the temperature from 30 to 70. It is 40. And here we need to disload below 50 degrees. So I will consider the least temperature as the room temperature as around 25 degrees. So this is going to be 50 minus 25. So this is 25. And here it is, we need to cool the reaction mass to 30 degrees. So the previous operation is 50. So we are going to take the delta T of 20 degrees. And coming to here, the heat the reaction mass to 50 degrees from 30. So again this is going to be 20 degrees. Here again we need to cool the reaction mass to 0 degrees from 50. So I'll take a delta T of 50 degrees. So these are only considerations, and based on your actual process you can take these things. So here in this case we are going to heat the reaction mass from 30 to 70. So there is no change of phase. So the latent heat is going to be 0. And the next one is distill out solvent completely under vacuum below 50 degrees. Here in this case we are going to distill out the solvent. Here the solvent that we have considered is water. Hence in this case the latent heat is going to be equal to that of water. It is going to be 540. And as it is going to be under vacuum, what will happen is the latent heat is going to further increase. However, I will be taking the value as standard, that is 540. But if you want to take the actual value, so you have to refer the steam tables so that you can understand what is the vacuum, what is the pressure, and depending on the pressure you can select the latent heat. And the next operation is cooling, so there is no phase transfer, so it's 0. Again, it is heat the reaction mass to 50 degrees from 30, so again it is 0. The next one is cooling to 0 to 5, again it is going to be 0. And coming to sensible heat load, so this is going to be mcb delta t. So here m is in kgs, followed by cp and then delta t. The same thing is going to be for all operations. Why? Because all operations involves heat transfer, like the sensible heat transfer. Coming to latent heat, here there is no latent heat involved, so this is 0. And coming to here, we are going to disload solvent, that is from liquid phase to vapor phase we are going to convert it by having some adequate heat transfer. In this case, we need to consider the latent heat also. So the latent heat is going to be, we need to take the volume, like the mass with respect to the distillate. Here in this case, we got a reaction mass volume of 1000 kgs. So let's say as this is complete distillation, I'll be taking almost 90% of distillate. That is 90% of reaction mass is going to be the distillate. So m is going to be 1000 multiplied with 0.9. That means 90% of the reaction mass I'm going to distill, and lambda is going to be the latent heat here. And the other operations, this doesn't involve any phase change, so these are going to be 0. And now the total heat load is going to be sensible heat load plus latent heat load. Okay. This is done. And now let's come to steam consumption. So steam consumption means, so we need to identify what are the heating operations. Why? Because for this heating operation, sometimes we will be using hot water as utility and sometimes we will be using steam as utility. But even though if you are going to use hot water as utility, and this hot water need to be, like the temperature of the hot water need to be increased by heating with steam only. So we have to consider like the heating operations which are involved with hot water also as steam as being used, like it's going to be secondary type of heating we are going to use for the hot water tub. So we are going to convert the total heat, like we are going to calculate the steam consumption from the total heat that is being utilized to rise the reaction mass temperature. In this case, like the first case is going to be 40,000 kilocalorie. So just we need to divide this heat load with 540 kilocalorie. Why? Because 1 kg of steam, like the latent heat of steam is going to be 540 kilocalorie. So just do this. And coming to the second operation, here also we got some heat load. As this is a heating operation, we are going to divide it with 540. And next one is cooling. As this is cooling, no need to calculate the steam. And again we got a heat, so just copy and paste here. This is going to be again cooling, so don't do anything. So this is the steam consumption. Now we need to calculate the cooling capacity. So here the cooling capacity is going to be only for the operations which involves cooling. Initial two operations are going to be heating, so no need to do that. And coming to the third operation, that is cool the reaction mass to 30 degrees centigrade. Here we have done some sensible heat transfer, that is cooling the reaction mass. So just divide this 20,000 kilocalorie with 3024 kilocalories. That means 1 TR equals to 3024 kilocalorie. And the next one is heat the reaction mass to 50 degrees centigrade from 30. So it's a heat transfer, but it's a heating, so no need to consider the TRs. And coming to the last one, here again it's a cooling, so we need to calculate the TR. So simply copy and paste. So this is how we need to calculate the cooling capacities. Now the question is, as the operations are going to be having cooling, we have calculated the TR. But coming to here, the distillation operation, as this is a distillation operation, we are going to heat the reaction mass inside the reactor, and again we are going to condense the vapors at a condenser end. So in such a case, the utility is being used at the condenser end also. That means a certain amount of cooling capacity is required at a condenser end. We need to consider that also. So in that case, let's do one thing. Condenser is a heat exchanger which is going to remove the latent heat from the vapors theoretically. So we'll take some advantage of that. So here the cooling capacity should be ideally this latent heat. That means the total latent heat divided by 3024. Why? Because whatever the energy that you are going to provide to the water to distill out at a reactor end need to be taken out from the condenser end, so that again the vapor will transform into liquid. So this I am going to divide with 3024. So here now let's see, it's almost 160 TR. This is very huge. And also let's try to add one more thing, that is, even though you are going to cool the vapor, again there will be some portion of sensible heat that is being done at the condenser end. That means you are going to distill out the solvent at 50 degrees, let's say. That means vapor is getting generated at 50 degrees. And if the vapor reaches the condenser, let's say the temperature is 50 degrees. So if you are able to remove the total latent heat at condenser, still the collection, I mean the distillate temperature is going to be at 50 degrees only. But if you see practically, the vapors that are going to be coming from a condenser is going to be very cooled. That means the condenser, first of all, it is going to condense the vapor, and then it is going to do certain sensible heat exchange also. So I'll be taking almost 10% of the total latent heat as a sensible heat just to compensate it. Sorry, it should be not 0.1, it should be 1.1. So it's going to be 176.79 TR. So this is how we have to prepare the heat loads. And now we have to do the costing for these heat loads. And now let's prepare a summary for this. The first one is we need to calculate the total steam consumption in kgs. So this is going to be summation of this total thing, 1057 kgs of steam, and here the total cooling capacity requirement. This is going to be in TR. This is going to be summation of the last column. And now let's see about the cost. Steam cost is going to be in INR per kg. Let's say this is approx 3 rupees. And TR cost, so this is going to be in INR per TR. Let's say this is approx 14 to 15 rupees. The TR cost depends upon the capacity of the chiller that is available, like the compressors that are being run in the chiller plant, and also the centrifugal pumps which are available near the cooling towers, depending upon their operational things, and also about the ammonia consumption. And considering these things, we are going to mention the TR cost. So it is going to be in the range of 14 to 15 rupees if it's a chill brine. So if it's a chilled water, again it is going to vary depending upon the compressor capacity, the chiller capacity, and all. So here I have taken as 14 rupees for TR, but you can take based on the availability at your site. So the total costs incurred are going to be the steam cost multiplied with steam price and TR cost multiplied with TR price. So it's almost 5,971 rupees. So this is about the heat loads. And let's come to the power calculations, the power consumption and costing. The first one is the equipments. The second one is the MOC tag number. So these are only general things. The next one is in terms of capacity. Again, it's going to be motor capacity or rating. Let's say this is in I'll take it in HPs, and here it's working duration in hours, and here the final power consumption in kilowatt hours. So we need to consider the reactors, the filters, the dryers, and also if any auxiliaries are there like the vacuum pump and all, so we need to consider those things also. So here the equipments that I have been used are reactor 1, reactor 2, ANFT 1, and a vacuum pump and a centrifugal pump where we will be transferring the reaction mass. The MOCs are going to be MACL, SS316. Okay, I'll be taking all these as SS316, and here the tag numbers are going to be R1, R2, AD1, VP1, CF1. The capacities that I'll be taking is around 3000 liter, 5000 liter, 2000 liter, and the vacuum pump is going to be approx 800 meter cube per hour capacity, and centrifugal is 10 meter cube per hour capacity. Okay, and now the motor capacities are going to be almost it's 5 HP, and this I'll be taking a 7.5 HP. Again, this is a 5 HP. For vacuum pump it's 25 HP, and centrifugal pump I'll be taking it as 5 HP. Okay, so usually what the engineers are going to do is, so the motor capacity they are initially convert this HP into kilowatts, and then simply they are going to multiply this kilowatts with the working hours. But it's not actually like it's not the practical case. Okay, I'll explain you how to take it. Let's consider these values like the working durations: 20, 25, 30, and 15 and 3. So these are the working durations that we have taken, and come to power consumption. So this usually we are going to calculate by using the basic formula like power in watts equals to VI cos phi. This will be using this formula. So as it's a commercial manufacturing and it's a commercial power supply, the voltage is going to be 440 volts. Okay, and coming to the power in amperes, so this should be equals to that of like the maximum amperes consumption should be equals to that of the motor capacity. Like if it's a 5 HP motor, let's take the power the current is going to be almost 5 amps. So I'll be multiplying this with this, then cos phi, this is nothing but a power factor, so we'll be taking it as 0.85 or 0.9. So it's nothing but how you are going to convert the DC into AC. Okay, so just two things. So these are going to be in watts, so just to convert these watts into kilowatts I'll be dividing with 1000. So now these are in kilowatts. Now let's multiply it with the working duration also here. Okay, so now you got it in kilowatt hours. Simple thing is, if you are going to apply this formula, you will be getting in watts. So just divide it with 1000. So you will be getting in kilowatts, and then just multiply it with the working duration. So you will be getting in kilowatt hours. And coming to the summary of power consumption and costings. So total power consumption in kilowatt hours. This is going to be summation of the last column. Approx 309.5 kilowatt hours. Next, unit cost of power. So this can be INR per kilowatt hour. So I'll take it as 10 rupees. So you can take from a like from your own state electricity distribution. Here I'll be taking only 10 INR, and the total power cost is going to be this 309.5 multiplied with the cost. So here you got a almost 3095 rupees, and in this we have to consider, like ideally we have to consider the utility pumps and also the vessel lamps or any type of other type of stationaries that you will be using. But the reason why we are going to avoid those things are, those are the common things, like the utility pumps or the vessel lamps are being available for all type of equipments commonly, so we will be not considering it here. And one more thing, if you are able to consider, compare the costing that we have prepared here to that of the finance stream, there will be a lot of difference. Why? Because let's say here you got a steam cost, and the steam cost we have considered is 3 rupees. Maybe if you are able to see the same price for the finance sheet, they'll be taking it in the range of 30 rupees or somewhere. And if it's a power cost unit, so they'll be taking in the range of 70 to 80 rupees. The reason is they'll be calculating the same thing for a total unit, like the total manufacturing unit that they'll be considering. Let's say if it's a power consumption, so they'll be taking the power consumed by the vessel lamps or the power consumed by the equipments or instruments that are being used in the offices. So these and all they are going to consider, and depending on that they are going to increase the cost. But ideally this is how we have to take. And the last one is manpower costs. So this is going to be very costly compared to other things. So first thing that we have to mention is the watch time cycle, and the next one is total manpower per shift, and the next one is shifts per day, and the next one is average pay per person involved. Let's say the batch time cycle is 10 days, and total manpower shift per shift is going to be 2 persons are allocated for this particular product, so I'll be taking it as 2. And total shifts per day, ideally it is going to be 3, but it should be 4. Why? Because one shift they'll be taking leave, leave in the sense they'll be taking week offs, so I'll consider total 4. And here the salary that I'll be taking is 30,000 INR per month, and this you can vary like the average pay. And I'll consider 30 days, so this is going to be 1000 INR per day. And now total manpower cost is going to be, in terms of INR, this is batch time cycle multiplied with the total shifts per day multiplied with total number of persons per shift and multiplied with the total INR per day for single person. It is going to be almost 80,000. Okay, now let's see the consolidated costs. So the total costs in INR, it is going to be the summation of manpower cost and the power cost and the utility cost. So it costs around 90,000, and let's say the total output is going to be 100 kgs, and the overhead costs are going to be like INR per kg of material manufactured. So this should be this total cost divided with the total output. That means for every 1 kg of material that you are going to produce, so you are going to have, you are going to pay almost 891 rupees. So this is the total overhead costs. So in the previous video we have seen about the raw material cost contributions. So if you are going to add the raw material cost contributions along with this overhead costs, you will be getting the appropriate manufacturing costs, that is RMCC plus the overhead costs. So this is how we have to calculate the overhead costs. I'll do one thing, I'll be sharing this sheet through Google Drive for your further reference. If anyone wants the sheet, you can download it for free. So thanks a lot for watching the video. If you have any questions, you can please reach to our mail ID, that is pharmacalci823@gmail.com. And if you like our content, please like and subscribe to our channel. Also you can share these videos with your dear ones. So thanks a lot.